Hi friends, today I shall be introducing you to one of the simplest yet one of the most useful and widely used data structure, the stack. A stack is a limited access linear list of homogeneous items in which access is allowed only at one point of the structure called the top of the stack. This means that data can be added or removed from the top only. A stack is usually used for temporary storage of data, and the only basic operations allowed on the stack are addition and deletion of elements. But even the insertion and deletion operations are done in a restricted fashion. One cannot randomly delete any element or insert new element in any location in the stack. The most recently element in the stack is the only one that can be retrieved or removed. Thus, if one wishes to retrieve an element inserted long ago, one must first remove all the elements that were inserted after the desired one. For example, if three elements A, B and C are added to the stack in that order, then the first element to be removed will be C, followed by B and A. Equivalently, we can say that the last element to be inserted into the stack will be the first to be removed. This strategy of removal and retrieval is referred as LIFO or last in first out. A stack can be visualized as a pile of plates in a spring loaded cafeteria stack. In such a stack, only the top plate is visible and accessible to the user. All other plates remain hidden. As new plates are added, each new plate becomes the top of the stack and hides each plate below. When the plate at the top is removed from the stack, the second plate becomes the top of the stack. Two important principles are illustrated by this metaphor. The last in first out principle is one. The second is the contents of the stack are hidden. Only the top plate is visible. So, to see what is on the third plate, the first and second plates will have to be removed. Another real life example of stacks is CDs in CD container. Only the last inserted CD is visible, and when a new CD is inserted, it becomes the new top. Other examples which are based on last in first out principle are vegetable stack, shuttlecocks in the container, pile of plates. We now look at the basic stack operations. As already mentioned, there are two basic operations that can be performed on a stack. Push. This operation inserts or adds data in the stack. The last pushed data becomes the top of the stack. Second operation is pop. This operation removes the most recently inserted element from the top of the stack. In addition, we can define another operation that can be performed on a stack. This operation is peek, which reads the data from the top of the stack without removing it. Some authors also call this operation as top. In this example, we see the contents of a stack as a series of push and pop operations take place. Initially, the stack is empty. Next, we push in 3 values 8, 14 and 12 in the stack. At the end of these 3 push operations, the value 12, which was last to be inserted, is at the top of the stack. Next, pop operation is executed twice and the values 12 and 14 are removed from the stack. Next, value 6 is inserted in the stack, and finally, pop operation is again executed twice to delete the values 6 and 8 and the stack becomes empty. Next, we look how the stacks and their basic operations are implemented. The stacks can be implemented by the use of arrays or linked lists. Today, we shall see how stacks can be implemented using arrays. The array implementation needs to maintain 2 pieces of information: an array to store the stack elements and the index of the top element in the array. Here is the structure used to implement the stack. In this example, the stack is used to store the characters, but it can suitably be modified to store items of other data types such as integers, strings or even more complex structures. The size of the stack is defined by macro stack size, which is taken as 10 in our case. Next, we see how the 3 basic operations push, pop and peek will be implemented. To implement these basic operations, we shall be using 3 supporting functions to initialize the stack, check if the stack is empty, check if the stack is full. These operations are implemented as follows. Before the stack can be used, it has to be initialized. Initialization of stack is quite simple. We just set the value of the variable top to -1. Top points to the address of the last element inserted into the stack. So, in case the stack is empty, top will be equal to -1. The function init is defined to initialize the stack. The function has one argument named s, which is a pointer to the structure stack. Instead of the stack, we have passed its address as the value of one of its member. Top gets modified in the function. The function empty checks if the stack is empty by examining the value of variable top. If top is -1, then the stack is empty. The function full checks if the stack is full by examining the value of top. If top equals maximum index of array storing the stack elements, then the function returns a non-zero value indicating true condition. The function push inserts a character x into the stack. Before adding the item to the stack, the function first checks if the stack is already full by calling the full function. If the stack is full, then error message is flagged and the program exits. This error condition when one tries to push a value into a stack that has no more free space available is known as stack overflow. The variable top is incremented by 1 and x is then inserted at array index top. The function pop removes the top element from the stack. Before deleting the element, the function first checks if the stack is not empty by calling the empty function. The value stored at index top is returned. The variable top is then decremented by 1. The function peek returns the value stored in the top element of the stack. As we can see, the function peek is same as function pop. The only difference is that the value of variable top is not changed in peek. This is a simple program to display the working of a stack by performing a series of push and pop operations. The program uses the structures and functions for the stack defined above. The state of stack after execution of every statement is also shown. As we see, after call to init function, the value of top is set to -1 and the stack is empty at that point. When the function push is called, the variable top is incremented to 0 and element A is stored at index 0 of items array. The next call to push increments top to 1 and stores B at index 1. The third call to push increments top to 2 and stores C at index 2. When the pop function is called, the value at index 2 is returned and top is decremented to 1. Next call to top function returns value B stored at index 1 and sets top to 0. One should note that elements B and C are still present in the items array, as we are not explicitly deleting an element from the array during the pop operation, even though the elements have been removed from the stack. In the array implementation of stacks, the value of top is manipulated instead of physical removal of values from the array. After the next push operation, element D is added to the stack and top becomes 1. After the next two pop operations, the top is set to -1 and the stack becomes empty. So, with this we come to the end of today's lecture. Today we had introduced the stack data structure. Stack we had seen is a simple data structure with very limited operations, but even with these limited operations, stack has great utility and is extensively used in different fields of computer science. The main strengths of stack are very simple data type, very fast, direct access to last element added. Though the main limitation of stack is a set of operations is very restricted. There is no access to elements other than last element, no searching, no iterating. The terms stack, push and pop can often be heard in daily conversation by computer professionals. Consider the following samples taken from the Hacker's Dictionary. I am afraid I have got real work to do, so this will have to be pushed way down on my stack. Here stack refers to the set of things a person has to do in the future. I haven't done it yet because every time I pop my stack, something new gets pushed. If a person says he or she has popped something from a stack, that means that he or she has finally finished working on it and can now remove it from the list of things hanging overhead. If you are interrupted several times in the middle of a conversation, one may say, my stack overflowed, means I forgot what we were talking about. The implication is that more items were pushed into the stack than could be remembered, so the least recent items were lost. In the next lectures, we shall be discussing the various applications of stacks in detail. In the end, I will thank all the viewers.